like to say a hello to everybody at the conference for historically underrepresented minorities in physics. I'm Matt Spidell, and I am going to give you a tour of the Wing 3 and some of the calibration labs in Boulder, Colorado here today. As much as NIST is a research organization, it is first and foremost an organization responsible for distributing standards, i.e. we measure stuff. So what you're looking at here are some power meters. These are laser power meters, and in a nutshell, you would care about this if you ever go and get laser eye surgery. You want to make sure that what you're having done to your eyes actually makes sense, and these are some of the instruments that distribute the measurements of laser power and energy out to commercial activities, and those commercial activities then distribute that out to various different other applications. Some of those applications, so everything from laser eye surgery to the telecom companies to defense applications. Now, the lasers that we work with span a wide variety of powers. We work all the way from just a few photons and photon counting activities all the way up to very large lasers. This is a more classic example of a flash tube and a flash tube excited ion laser of some flavor from the 60s when lasers were first invented. And this is probably one of the earliest examples that we have of something used in our calibration program. A modern high-power laser is something a little bit more like an appliance that you might find in the kitchen, with the light traveling through those yellow fibers up through our ceiling and down through, and it comes into a small head here. Now, with that head about the size of a Coke bottle, one might not assume that this is anything particularly terrifying. However, this particular laser is sufficient to burn a hole in a brick in about 3 or 4 seconds. This is basically like a lightsaber. Not that you'd ever want to handhold this thing or be even in the same room with it when it's running. We have it guarded very well behind some pretty decent barriers just for safety purposes. Looking down the bench here, this is a setup for calibrating the power coming out of this source that I've just shown you, and determining, okay, we know how much power is coming out of it. Now let's bring in a customer meter and determine how much power it is reporting versus how much power we're actually imparting to it. With those two values, we develop a calibration factor. This is one of the primary standards that I've actually opened up here, and the way that these work is relatively simple. We have a thermometer that is built around the circumference of that black absorber there, and what we want to do is correlate the temperature rise that we see on that thermometer to the amount of energy that we inject electrically, because we can measure electrical energy to an extreme degree of accuracy. We inject a known amount of electrical energy and we measure the temperature rise. We then dump in an unknown amount of optical energy, laser light, and we observe the temperature rise. By correlating the temperature rise for the known amount of electrically injected energy to the temperature rise observed for the unknown amount of optical energy, we can determine the amount of optical energy that is imparted to this equipment. This is actually torn apart right now because I'm trying to determine its absorptivity, the absorptivity of this instrument, which is quite old. As you can see by the aging on that case, it's about a 30 or 40-year-old instrument, and it still works quite well. However, we want to know a little bit more about how this was operating, so we've got it torn apart here, and the apparatus that I have here, this is a device that I've built for measuring the absorptivity of things that are very, very dark, and I'm going to open this up for you real quick here. This is called an ingrading sphere, and just like the mathematical operation that you all know and love, it takes the light that is incident and averages it about the entire inside of the sphere. That allows us to get an average and remove the spatial non-uniformities from the things that we're measuring. This is a research project that we picked up over the last year and have been conducting and assembling during the pandemic activities. This is actually a three-dimensionally printed prototype of something that's eventually going to get manufactured out of a better anodized aluminum surface with a gold plating on top of that. This is a lab where we work on various different coating technologies. The coating that we've been working on in this lab pretty aggressively for the last few years, something called carbon nanotube blacks. This is basically the blackest thing that humankind can make. It absorbs 99.999 and then some percent of the light incident on it. When you throw one of these things up against a wall, it looks like you've just put a hole in that wall, a little bit like a cartoon. We take these materials and we try to coat detectors with them, and this is a detector that has been coated, and you can see that that sample basically looks like a little hole punch in there. All the light disappears there. When I say that these samples are black, they absorb pretty much all the light across the visible spectrum out to the infrared and even beyond that, out to what you call extreme shortwave radio, or terahertz, if you want to think about it that way. Now, this particular lab is a good example on where one's after-school activities might actually come in and awful useful. This is a lot of handwork in here, trying to get the coatings to stick to surfaces. We have been using a lot of different techniques, from airbrushing to acid liftoff to trying to bond stuff on with various different adhesives. It's the kind of thing that you'd actually pick up, of all things, doing modeling, such as building small model vehicles or some such thing. It's a case where one's personal activities can actually translate over to some real results. In taking on a career in science, you're going to have to be prepared for an awful lot of tedium. This particular device here I like to bring up when I talk about the time that it takes to do science, because getting this particular instrument to run, you might spend a good half a day to a full day tweaking every single knob on this thing and still not get it to work right. This is a laser that we use for developing various different wavelengths in the infrared. We start out with that green wavelength there that you see bouncing off those mirrors, directed over to another experiment right now. And it can get pumped through this particular system and it'll generate other wavelengths. That's just a tool. It can take a day just to get the hammer for your experiment to work. This is actually just an appliance when it's working well. The actual science part can take an awful lot longer, and it takes an awful lot more effort and attention to detail and time, and you're going to pay for it with an awful lot more frustration. There's no way around that. It's just part of the job. In spite of the time and effort and energy and frustration that it can take, the results eventually do pay off if you work at it long enough. I'm going to take you to one of the laboratories where we have equipment that we have put together for satellites. On this table are examples of instruments, in some cases, that have flown on a satellite to go and measure the Earth's climate budget. The instrument at the center of the frame here, where it says SSI flight, a copy of it was packed in that case where it went out and got assembled onto a satellite, which eventually got launched last year, I think. That was the Compact Total Solar Irradiance Monitor, which, again, that's trying to figure out how much energy is coming into the Earth. That's just one of a number of projects. This is our bragging table, as it were. Everything from patents, papers that have come out of that hard work, along with one of our items that broke in the most spectacular way. These things happen as well. You got to take the pain along with the projects that are actually going to work out. There's no way through it that's easy. You're going to work very hard, and it's going to be a very, very hard journey to get results. Eventually you will get some, and who knows, one of those results might even fly in the stars, as it were. So from the NIST Boulder campus, I'd like to wish you all a good luck in your careers, and maybe y'all can join us out here one day.